thank you for accepting our invitation for the seminar. Dr. Breno Raphaldini has obtained his bachelor and PhD degree in geophysics at the University of Sao Paulo, and he is currently a postdoc at HAO NCAR, working with Masumi Dikpati. His research interests are solar physics, geophysical fluid dynamics, and nonlinear dynamics. He has experience with Rossby waves, both in the Sun and the Earth, and is also working on a winding parameter measurement of twist for emerging active regions that he will talk about today. So I will pass the Zoom to Breno very soon. But just one note, during the talk, if you have questions, please be brave to ask it at the time, and you don't have to wait until the end of the talk to ask the question for discussion. So thank you, Breno. I will pass on to you.
So yeah, I'd like to thank Dr. Shen and Amy for inviting me for this talk. And today I'll talk about the topology of magnetic fields in active regions, and in particular introduce this new quantity called magnetic winding that is a measure of topology of magnetic fields. So this work was joint work with Chris Pryor and from the University of Durham University, and David McTaggart from the University of Glasgow. So this is the outline of the talk. I'll just say a few words about magnetic activity of the sun, introduce topological concepts such as the magnetic Ellistian winding, and I will use show how magnetic winding can be used to characterize twisting in emergent flux tubes, and I'll also show how magnetic winding can be used to maybe predict flare events. So you know that the magnetic fields in the sun are generated by a dynamo process, and in particular we believe that a very strong magnetic fields may be generated in the tachocline region that is at the bottom of the convection zone. And once these strong magnetic fields become buoyant, they can arise through the convection zone and eventually emerge through the photosphere. So once these tubes of magnetic field arise, they manifest themselves in the form of active regions and sunspots, like as shown here. And one of the important aspects of understanding the physics of emerging magnetic fields is that explosive events associated with the emergence of magnetic fields, such as coronal mass ejections events and flares, can cause several impacts, such as impacts in telecommunications, in satellites, and energy transmission and ecology. So it's important to understand the physics and maybe try with this understanding to predict these events. So the morphology of magnetic fields in active regions, they can be classified according to their the complexity of their morphology, and it's known that strong flare events are correlated with more complex magnetic field configurations. In particular, for instance, 80% of the X-class flares are associated with delta regions. But a question that I would like to pose is it possible to quantify this complexity in the morphology in terms of the topology of magnetic fields? So the strategy, what I'll do is to introduce some topological concepts that are correlated with the complexity of magnetic fields in active regions. So it's just one example of a very flare productive active region, and show how complex this morphologies. So one of the most traditional topological concepts used in the characterization of magnetic fields in active regions is the magnetic helicity. That is defined as the integral over a volume of the dot product of the vector magnetic field vector potential with the magnetic field. This is an important quantity in magnetohydrodynamics. One of the important properties of helicity is that it's a conserved quantity in ideal MHD, and it has a topological interpretation in terms of what is called Gauss linking number, which is if you think of pairs of closed loops of magnetic fields, this number counts the number of crossings between the two field lines. So the helicity is the Gauss linking number weighted by magnetic field strength. So here is what an illustration how it works. For instance, here you have two crossings of this loop of magnetic field across the surface defined by the other magnetic field line. So the helicity is just the number of crossings times the flux, the intensity of the magnetic field. In practice, instead of calculating the helicity, what is usually done in the characterization of magnetic fields in active regions is to calculate the so-called relative helicity, which is the helicity relative to a potential magnetic field. So the reason for doing this is because the magnetic field potential is defined up to I mean it has a gauge here, so it can be chosen, that can be chosen arbitrarily. So when we calculate a relative helicity, we remove this ambiguity, and so in order to calculate the helicity, we can use the Biot-Savart law to calculate the vector potential. And one way to calculate the relative helicity from measurements of magnetogram measurements of magnetic fields in active region is to integrate over the surface of the active region and calculate the flux of helicity, and calculate then, once we know the change in time of relative helicity, we can integrate this and obtain the accumulation of relative helicity. So this quantity can be used to characterize flare activity. I mean, it has been calculated before. There are several papers that correlate the accumulation of helicity to the level of activity. For instance, this is one particular paper doing this. But then a question arises is that, of course, magnetic helicity is a measure of topology, but is it a good measure in the sense that, does it measure the topology evenly in the domain of the active region? And the answer is probably not, because since the relative helicity is weighted by the strength of the magnetic field, the fact that the distribution of magnetic fields in an active region is characterized by a distribution with very heavy tail, it will I mean what will happen is that the helicity will be representative by of this the subregions of the active region with very strong magnetic fields. For instance, here is an example of a magnetogram, and this is the distribution of values of magnetic fields. And you can see that comparing this histogram with a Gaussian distribution, the actual distribution has a very heavy tail, meaning that if we calculate the helicity will give a very high weight to sub-regions where the magnetic field is very strong. So, and here, for instance, you can see how the helicity is actually dominated by the regions of a very strong magnetic field. So one way to overcome this is to renormalize the formula of the helicity by replacing the value of the magnetic fields by 1. But to be more precise, you take regions where it's minus, where it's negative, the radial magnetic field is negative, you replace by -1. If it's positive, you replace by 1. If it's 0, you just keep it 0. And this is the actual definition of magnetic winding. Magnetic winding is a renormalization of the helicity, replacing the strength of the magnetic field by ±1, depending on if the magnetic field is positive or negative. So then the topological interpretation of magnetic winding it's actually the Gauss linking number, which will only count only the number of crossings between pairs of field lines. But unlike helicity is not weighted by magnetic field strength now. So in order to show an application of the magnetic winding, I will first introduce the composition that can be performed in both helicity and winding, which is to decompose the contributions of the helicity and winding due to vertical plasma motions, which is called the emergence term of the helicity or winding, and the term due to horizontal plasma motions, which is called the braid term. And this can be done both for helicity and winding. And here I show, I illustrate the difference between both. So once you have an evolving magnetic field, you see that here is one example illustrating the effect of horizontal plasma motions. So you can see that you take the red magnetic field line as fixed, and the blue line is moving in time. So what happens is that the angle between these magnetic field lines will change due to advection of the magnetic field lines due to horizontal plasma motions. On the other hand, if you have a magnetic, for instance, a tube of magnetic field emerging, what will happen is that the vertical plasma motion will change the foot point, the point where the magnetic field line crosses the plane of the photosphere, and by doing this, it will also change this angle between pairs of magnetic field lines, which will change the value of the helicity or winding. And this decomposition can be very useful. Here I show a typical, for instance, a typical scenario is that In between foot points, you usually have a stronger vertical motion because the magnetic field is first emerging here in the middle, but in the foot points, the change in helicity and winding is usually dominated by horizontal plasma motions. And here I show in one example of actual densities of helicity and winding for these particular active regions, how it manifests. So here you see that here are the foot points. So the helicity is usually dominated by, I mean, in regions where the magnetic field is strong, and winding is dominated by, I mean, is strong, usually in the middle of in between the foot points. So a typical scenario is that usually helicity is dominated by, I mean, changes in helicity are dominated by horizontal plasma motions, whereas changes in the winding are dominated by vertical plasma motions. So with this, we can show an application which is to discern between, differentiate between pre-twisted or post-twisted magnetic field configuration. So the question is, once a magnetic field is emerging in an active region, we want to evaluate if this if the twisting of the magnetic field lines occur prior to the emergence or post-emergence. So in order to do this, we performed a 3D MHD simulation with a compressible in a compressible scenario, where we place a bundle of magnetic field below the plane of the photosphere, and let the convection act on this magnetic field until it arises. And then we evaluate how each term of the associated with magnetic winding behaves during the emergence. So here is the result. So in blue, it's the total the blue curve represents the total winding, and this yellow curve represents the emergence term, which is the term due to vertical plasma motion. And in red is the contribution to the winding of the horizontal plasma motion. So you see that the winding can be pretty much explained by the vertical term of the plasma motion. So this gives us some confidence to apply this to magnetogram data of actual active regions. So here is, in this case, we determine that, we know a priori that this magnetic field line emerged pre-twisted. But then we want to see if we can conclude this from magnetogram measurements. So here is one particular active region, AR 11318, and we see that again, the winding here is dominated by the emergence term, which is the term due to vertical plasma motions. So in this case, for this active region, we conclude that the magnetic field emerged pre-twisted, because it is when it arises, it already has a twist. And in comparison, we can calculate the same decomposition for helicity, and when we see that it's actually dominated by the horizontal, the changes in helicity are actually dominated by horizontal plasma motion. what this says is that the helicity cannot be used to differentiate between pre and post twisting during the emergence. And here you see the densities of winding and helicity. So here the helicity is dominated by the braid motion, which is the horizontal term, and the winding is dominated by the emergence term, which is the term due to vertical plasma motion. So here we show for another an active region, and again, it's pretty much dominated. I mean, the winding is pretty much dominated by the emergence term, which is the term due to vertical plasma motion, which indicates that this is also pre-twisted. And again, showing the composition for the helicity, it shows that the helicity is actually dominated by the braid term, the term due to horizontal plasma motions here. So again, it cannot be used to differentiate between pre and post. Someone has a question?
Yes, hi.
Hi.
Yeah, here we are.
Hi, Breno. Quick question about the simulation you were showing a couple of slides earlier. May I know which tool or which software did you use for that OpenFOAM, or just wondering how you did, which tool you used that?
Oh, because I forgot that it's an open source. I mean, you mean the name of the code?
Yeah, OpenFOAM, or since you're mentioning open source, I'm just wondering.
Yeah, I think it's open, actually, because it wasn't me, it was David who performed the simulation. I think it was because I just performed the observational part, but I think it's OpenFlow, yes. But okay. For sure it's an open source code. Yeah.
Got it. Thank you.
And it's this is a compressible a compressible simulation with a Newtonian cooling. It's not radiated. It doesn't have a radiated.
Breno, I have another question.
Yes.
And I remember the helicity density does not have physical meaning because that's depend on gauge. So when you discuss,
this is the relative helicity.
Right, even relative helicity density does not have meaning. I mean, when you talk about the distribution of helicity density, that depends on gauge. So you are showing the map of distribution of density, helicity density.
Yes.
Which that one. The bottom two panels. I'm afraid maybe that does not make a perfect sense.
Yeah, I mean as I said, this is a relative helicity.
Right,
but you can.
It doesn't matter relative or helicity. Simply the helicity density.
Yes.
Distribution depend on the gauge you choose to calculate the helicity density. So you can talk about the single number, that's okay. But when you talk about the distribution,
yes,
that might not have physical meaning. So that's my understanding. Probably I could be wrong.
Yeah, I would have to think, but I believe the relative helicity, even the density does not depend on gauge, but I would have to think.
You can
I think so.
Check Perry paper in 2014 or 2015. He actually demonstrates the helicity density distribution is depending on the gauge.
Oh, maybe I can, if you can send me the link, I would like to have a look on this paper. But okay, thank you. More questions? Okay, so so I would like to proceed by showing an application that makes use of further decomposition, which is to decompose the magnetic fields into a potential and current carrying part. So this is inspired by work by Pariat and collaborators, where they show that flare activity can be, I mean, the amount of helicity due to current carrying field is a good predictor for flare activity. So they showed this first in simulations shown here, but they also showed this in observations. So in order to evaluate the relative contribution of potential and current carrying magnetic fields, we define two quantities. That is a global measure of imbalance between the potential current carrying magnetic fields and a local measure. So the difference is that for this one, we first integrate the current carrying terms and the potential terms throughout the whole domain, and then subtract. But for the local quantity, we integrate this point by point. So in case where there are several changes in sign throughout the domain, this is actually more a better quantity, because it would take into account I mean the sign of the quantity. So just to complement, so when these quantities are positive, it means that they're dominated by current carrying field, and when they are negative, they're dominated by potential field. So then we apply this decomposition in the magnetic winding for a series of active regions. First, for a non-flaring one, we show that here we calculate the time evolution of the current carrying part of the magnetic winding in the potential part. So once we calculate the difference between both, which are those imbalanced quantities that are those, we see that this is negative, which means that they are dominated by potential field, and this correlates with the fact that it doesn't flare in this case. Here we show another one with moderate, small flare activity, only 1C class flare. And this actually shows that these quantities actually change sign. So when we calculate the local imbalance, it keeps growing, and while the global quantity is first positive and then negative, which means that there are changes in sign throughout the domain. But in nevertheless, there is a small imbalance that the local quantity says that it tends towards the current carrying field, and it has a moderate flare activity. So then we show another active region with a very strong flare activity with 28 C class flares, 4 M class flares, and 4 M class flares and 1 X class flare, which is AR 11158. And here we calculate these quantities. So here, as I mentioned before, And when you compare these quantities integrated in the domain, it seems that the potential term dominates. But what happens, in fact, is that the current carrying part is actually stronger if you compare the distributions. And when you actually integrate point by point, you see that it's actually dominated by current carrying field, which is that's why the local quantity is positive here, and it correlates with the fact that it represents 1 X class flare and 3 and 4 M class flares. So and then when we see the actual time series of this not the accumulated quantities, but the time series of the flux, you see that before a strong flares in the winding, you can see strong peaks in the influx of winding that correlate with the strongest flares. So we go on to another active region, which is the most prolific during solar cycle 24, with 4X class flares, 27 M class flares, and 55 C class flares, which is AR 12673. And in this case, when you calculate the quantities, you see that it's very strongly dominated by current carrying field. And yeah, you can see here where the strong flares occur. And again, you can see that the strong flares are preceded, or I mean, at least the X class flare here, the strongest one, the X9 flare, is preceded by a very, very strong influx of winding. And we also investigated how the distribution distribution of winding occurs during this strongest flares, the X9 flare. We see here because oh, sorry, just 1 second. Because I cannot see my screen. Oh, no. Okay. So here in the middle is the time when this spike in winding occurs. You see that the scale here changes. It's actually 20 times stronger than before and after. So here is just a difference of hours. You see here, and you see that there's a very strong signal in the winding here that is I mean, at least 1 order of magnitude stronger than before and after. And we, by investigating the velocity and magnetic field configuration here, we see that this strong signal actually happened due to submergence event along the magnetic field inversion line, which is I show here. So this is where this strong spike of magnetic winding originates from. And here you can see that it's actually happening in a inversion line. So the question that also arises here is whether we can use this for a prediction of flares. So here, I mean, this is still ongoing work, but in order to illustrate the potential application of magnetic winding to prediction of flares, we here show for this active region 12673, the one that produced very strong. I mean, no, this is 11158. Sorry. We calculate a signal that is representative of the flare energy, And we correlate this with this imbalance in the winding. We see that the strong flares are preceded by the rise in the imbalance of the winding, which also occurs in the helicity. But the scenario that we found is that before the start of the flare activity, there's one spike in winding, and then it rises again before the strong flare activity. So this is still working in progress. Then we are currently applying this for several other activations. So I'll go on with the conclusion. So the winding is a useful tool in the analysis of active regions. It provides evidence for emergence of pre-twisting in the emergence of magnetic fields in active regions, and it's a good indicator of the eruptivity in active regions, and maybe can be applied to predictions as well. So before I finish, I would like to advertise the code that we developed for the calculation of magnetic helicity and winding, which is currently available at this page here. It's very easy to use. You just have to, you have to have installed SumPy, but you only provide the sharp number of the active region, the start time, the end time, and then it will automatically download the magnetograms and calculate everything. So here are the references, and I would like to thank you for the.
Thank you to Breno for the nice presentation, and well, we'll still have some time for questions and discussions.
Yes, it's. Any questions?
Well, if no question, I see there are already questions asked in the
Oh yes.
I heard someone. Is it from the Cyprus or something? I heard someone talking. Well, I am talking. Sorry about that. Okay. If no one have questions, maybe we can end up early as well. But let me make sure. Any questions? Because I thought I heard something just now. Okay, if no question, let's thank our speaker today, Breno, for the very nice presentation. If there's any follow-up questions afterwards, please email Breno or me and for follow-up discussions. Let's thank Breno again, and thank you for everyone for attending the seminar today.
Thank
See you
you.
next month.
Thank you.
Thank you.